In this workflow, we want to solve a classification problem. Using the airline dataset, we want to predict whether or not a flight departure from Chicago's airport will be delayed. You can download the dataset from this link. We integrated the original data with calendar and weather information taken from Google Calendar API and from the Weather Station repository. For the purpose of this video, which focuses on data preparation, we assume that we have already read the airline dataset and blended it with weather and calendar information. We will use different advanced ETL and machine learning-based pre-processing techniques to detect and delete outliers, reduce dimensionality, generate new features, and discretize and normalize the data. Let's start with the data preparation, in particular with the outlier detection. There are many possible strategies to detect outliers. Here we implemented two, a knowledge-based strategy and a statistics-based strategy. In the upper branch, we use a box plot. The data points exceeding the whiskers of the box plot are assumed to be statistical outliers. In the lower branch, a set of knowledge-based rules detects extra domain values in the departure time column. We move on to dimensionality reduction by removing meaningless columns. Again, there are many ways to reduce dimensionality. Here we show only a few. Other strategies and their implementation in Knime can be found in this white paper here. In this workflow, we apply 4 dimensionality reduction strategies. We remove a column if the percentage of missing values is higher than 95%, or if the standard deviation or the skewness is smaller than 0.1, or if it is highly correlated to another column of the dataset. Let's take a look now at the feature generation and missing value part. We start by generating some new features from the raw data. Knime provides a number of nodes to create new features. Here, for example, we use the binning node to determine the flight distance category. Another example is using the group by node to calculate the average delay of each single airplane. The math formula and the rule engine node are also great help in generating new features. Classic new features are tool operational and/or customer behavioral features, for example. They can usually be created with a combination of the group by, math formula, and rule engine nodes. In the second meta node of this pre-processing part, we focus on how to handle missing values and nominal value discretization. Here the key nodes are the missing value node and the category to number node. The missing value node provides different strategies to impute missing values. A list of all options can be found in the node configuration window and of course depend on the data type. For numerical values, we can use the mean, the maximum, or a fixed value, for example, while for nominal values, we could use the most frequent value, the next value, or another fixed value. These settings apply to all numerical and all nominal values in the dataset. However, we can also proceed with imputing missing values on a single column. In this workflow, first we delete all rows with a missing value in the dependent variable, in our case, the departure delay. Then we impute missing values in all other columns with a fixed value, 0 for numbers and unknown for strings. In order to create a training set and a test set, we use the row splitter node. We use the 2007 data for training and the 2008 data for testing. We could also have used a partitioning node for this operation. Since we are going to apply PCA and SVD later on as further dimensionality reduction techniques, we need to normalize the data. This is achieved with the normalizer node. So let's move on now to the last subsection of the ETL and preprocessing part, automatic dimensionality reduction and feature selection. We implemented the principal component analysis, PCA for short, and singular value decomposition, SVD for short, as 2 possible automatic dimensionality reduction techniques. For the PCA, we are using a Knime native node. For the SVD, we use the Python integration. The latest Knime Analytics platform release has significantly improved the Python support. Knime now supports Python 2 and Python 3, as we can see in the node repository. In the meta node, which uses Python to implement the SVD, the Python learner node trains the SVD model. The Python predictor nodes apply this model to the test and training sets to reduce their dimensionality. In this way, we can take advantage of the Python Scikit machine learning libraries to train and apply any analytics and data science model. Another way to perform feature selection and row reduction is to use machine learning algorithms. If we want to reduce rows, we can use a k-means algorithm to group flights with departure delays in 100 clusters, while flights that have had no departure delays are grouped into another 100 clusters. We could do the same using the k-nearest neighbor algorithm. If we want to reduce the number of columns, we could use the random forest. Based on the candidate and split statistics produced by the algorithm, we can measure the importance of each one of the input features and then decide whether or not to remove them. Here on the other side, we proceed with backward feature elimination and here with the forward feature selection. For both strategies, Knime provides a metanode template in the node repository. The metanode template offers a default machine learning algorithm that can easily be changed. The last node of the metanode template is the feature selection filter node. It shows how many and which features are needed to get a given accuracy. Here we need only 4 features for an accuracy of 90% on the test set.